Welcome back to BE 110 Continuum Mechanics. We need to review matrices and vectors because in continuum mechanics we're going to learn about tensors. And a tensor is to a square matrix what a vector is to a column matrix. Now, a vector is a physical quantity, so a column matrix can represent the components of that vector provided we specify a particular frame of reference, particular coordinate system. If we choose a different coordinate system, since the vector is a physical quantity, it will have different components because changing the frame of reference or changing the observer can't affect the physical quantity, it must therefore affect the components. Well, the same is true of a tensor. A tensor is a physical quantity whose components in a given frame of reference can be represented in a matrix, or more specifically, a rank 2 tensor in three-dimensional space can be represented by the components of a 3x3 matrix. So we're going to review ideas about matrices and vectors that you've heard before, but I want you to think about these ideas in the context that these properties of matrices that we discover will frequently be properties of tensors, which means that some of the familiar properties of matrices that we've learned about are actually physical quantities. They represent something that has meaning beyond just the mathematical definition. So let's start with an orthonormal basis. So that means an orthogonal set of right-handed Cartesian coordinates with an origin O and unit base vectors in the x, y, z directions, or x1, x2, x3 directions, labeled E1, E2, and E3. So now if we have a vector V, then we can write that vector as being the sum of V1 times E1 plus V2 times E2 plus V3 times E3. The vector V has components V1, V2, and V3 with respect to this particular orthonormal basis that we can express in a column matrix that we could call V. So here the column matrix V has components V1, V2, and V3, or VI for short. Now, a property of a square matrix is that it transforms one column matrix to another column matrix. For example, A times X equals B. If A is an n by n matrix and X is an n by 1 matrix, then B would be an m by 1 matrix. In continuum mechanics, m and n are invariably 3. Therefore, A would be square, and therefore B would also be a 3 by 1 column matrix. In other words, the matrix A could take the components of one vector and give you the components of another vector. So, analogously, a rank 2 tensor transforms one vector to another vector. So this is another way of telling us that the tensor A is the tensor that maps vector x to vector b, or that the tensor A is defined by two vectors x and b. So now let's review some matrix notations that you're familiar with already. So the matrix A would have components Aij, where I refers to the row. So this matrix would go from A11 to A1n in row 1 through to AM1 to AMN in row M. So it has m rows and n columns. Similarly, an n by 1 column matrix X would have n rows with components x1 through xn. The row matrix X transpose would be a 1 by n matrix with one row and x1 through xn in the columns. So some properties of matrices like these would be symmetry, for example. So A would be a symmetric matrix if the components of A were equal to the components of A transpose. In other words, if we swap the rows and the columns, we get the same matrix, or in index notation, Aij equals Aji. The matrix A would be skew or antisymmetric if the components of A were equal to the negative of the components of A transpose, or Aij is equal to negative Aji. As you know, we can multiply two matrices. So the products of matrix A and B could be C, and if A was M by N and B was N by P, then C would be M by P. We could write this in index notation as the components Ij of C would be the sum from k equals 1 to n of Aik times Bkj. It's important to remember that this definition of matrix multiplication is not commutative. A times B is not equal to B times A. An important matrix that we use in matrix algebra is the unit or identity matrix, which is often denoted by I or sometimes 1, and has components of 1 along the diagonal and zeros on all the off-diagonal components. In continuum mechanics, we refer to the components of the identity matrix as delta Ij, where delta Ij is known as the Kronecker delta. So the Kronecker delta is the operator that is equal to 1 when I equals j, and 0 when I is not equal to j. A simple property of delta Ij is it has the effect of substituting indices. For example, let's consider the sum from j equals 1 to 3 of delta Ij times Ajk. This is just multiplying the identity matrix by A, so we still get A, but now the indices would be Aik, because delta Ij has switched the index j for the index I. Another property of a matrix, of a square matrix, is the sum of the diagonal components, which is known as the trace of the matrix. So the trace of A is the sum from I equals 1 to n of Aii being the diagonal components, or A11 plus A22 through to ANN. For a 3 by 3 identity matrix, the trace of I would equal 3. 1 plus 1 plus 1. So the determinant is another familiar property of a matrix. And for the 3 by 3 matrix A, we could write the determinant as this nested summation, 1 over 6 times the sum from I equals 1 to 3, j equals 1 to 3, k equals 1 to 3, r equals 1 to 3, s equals 1 to 3, and t equals 1 to 3, times special symbol Eijk times ERST times AIR, AJS, AKT. So this special symbol, which enables us to write the determinant in this indicial notation, is called the alternating, or more commonly, the permutation symbol. You can probably imagine it's mostly 0, except for special combinations of I, j, and k. So the first one is that if I, j, and k are all different and are an even permutation of the numbers 1, 2, and 3. In other words, I, j, k are 1, 2, 3, or keeping those in the right order but cycling, 2, 3, 1, or 3, 1, 2. In that case, Eijk is plus 1. If Eijk is an odd permutation of 1, 2, 3, it's negative 1. So an odd permutation would be like an even permutation of 3, 2, 1. Any other values of I, j, and k, namely when I or j or k have any two indices that are the same will be 0. So from this we can say that eijk must equal ejki must equal ekij, which are all cyclic positive permutations, and equal to negative ekji, negative ejik, and negative eijk. If the determinant of A is not equal to 0 for the square matrix A, then we know that the inverse of A must exist. A is said to be non-singular. Now let's consider an important property of matrices that we make use of a lot in continuum mechanics, and that property is called orthogonality. To remind you, a square matrix Q is orthogonal if its inverse is equal to its transpose. In other words, we can write that Q times its transpose, or Q transpose times Q, must equal I, the identity matrix. This means that the determinant of Q is either 1 or negative 1. If Q is orthogonal and the determinant of Q is positive 1, then Q is called a proper orthogonal matrix. So a proper orthogonal matrix is a rotation. If the determinant was negative 1, there could be a reflection in that orthogonal transformation. But its proper orthogonal transformations are the ones that we're mostly interested in continuum mechanics. So as an exercise, you can show easily that if Q1 and Q2 are orthogonal matrices, their product Q1 times Q2 is also orthogonal. Now to this point, we've been using a summation symbol for the indices. Because these are so frequent when we use these index notations, in continuum mechanics, a convention is used that was developed by Einstein, whereby wherever an index is repeated once, for example, the index I equals 1 to 3, then the summation is automatically implied and you don't need the summation symbol. So for example, we can write that the trace of A is equal to AII instead of writing the sum from I equals 1 to 3 of AII. And similarly, we could write delta ij times ajk is equal to aik instead of including the summation from I equals 1 up from j equals 1 to 3 in this case. So I in the first example or j in the second example are called dummy indices. They're the ones that are summed. Here, the summation index in the matrix multiplication aik bkj is k, so the implied sum is over k equals 1 to 3. The trace of the product AB would be the scalar, which would be the sum of the diagonals of CII, which would be CKK, which is AIK BKI. Notice if there's no free indices left, then we don't have a vector or matrix property anymore, we have a scalar. If we have two column matrices A and little b, whose components are A1, A2, and A3, then A transpose B would be the scalar product AIBI, namely A1B1 plus A2B2 plus A3B3. If Q is orthogonal, and we multiply Q by Y to get X, then we must be able to say that Y is Q inverse X, which would be Q transpose X. Or in other words, yi equals qji xj. So notice now the summed index is the first index of Q rather than second, because this is the matrix multiplication Q transpose times X, not Q times X. So many, perhaps all of the matrix identities that you've seen before are also able to be derived in index notation by taking advantage of the so-called E-delta identities. So one thing I'll ask you to do is to take a look at a handout of these E-delta identities and review them. I don't think these are really something you need to memorize and understand. The ideas are ideas you've already seen before, but these are the algebraic tools that enable you to derive matrix relations using index notations, which you probably haven't seen before. So of course, another important properties of matrices are eigenvalues and eigenvectors. So to review, for the matrix A that is square and the column matrix X, we can define the eigenvalues and eigenvectors by the equations AX equals lambda x, where lambda is a scalar. And this therefore implies that the new matrix A minus lambda I times x must equal 0. And this equation can only have a non-trivial solution if the determinant of that matrix A minus lambda I is equal to 0. Now the determinant is a scalar quantity, so this is a scalar equation, and that scalar equation is called the characteristic equation for A. And if A is a 3 by 3 square matrix, then its characteristic equation would be cubic in lambda, meaning that it would have 3 possible solutions or roots. And of course, these roots, lambda 1, lambda 2, lambda 3, are the eigenvalues. So knowing that lambda 1, lambda 2, lambda 3 are the eigenvalues of the characteristic equation, we can write that the characteristic equation must look like lambda 1 minus lambda, lambda 2 minus lambda, times lambda 3 minus lambda. If we look at the constant term in this, we could deduce that the determinant of A must actually be the product lambda 1, lambda 2, lambda 3. Now, if all the eigenvalues are real, then that means that our original equation, AX equals lambda x, has non-trivial solutions, x1, x2, and x3, and those, of course, are the eigenvectors associated with the 3 eigenvalues, lambda 1, lambda 2, and lambda 3. So as an exercise, perhaps you could refresh your memory about eigenvalues and eigenvectors by solving this simple problem. Find the eigenvalues and eigenvectors of the matrix A with components 2, 0, 0, 0, 3, 4, and 4, 0, 4, negative 3. It's easy to show that the eigenvalues are, for this problem, are 5, 2, and negative 5. And the first eigenvector is 1 over root 5, 0, 2, 1. I'll let you work out the other two. Notice we divided the components 0, 2, 1 by the square root of 5 so that the eigenvector would be normalized, which is conventional. If A is real and symmetric, then the eigenvalues and eigenvectors are also real. The eigenvalues don't have to be distinct. They don't have to be different numbers. But if they are, then it's easy to show that the eigenvectors are orthogonal. So start with the definition, ax1 equals lambda x1, or lambda 1 x1 to be more precise. Then pre-multiply this expression by x2 transpose to give us x2 transpose a x1 is equal to x2 transpose lambda 1 x1, and we'll label this equation A. Similarly, we can pre-multiply the eigenvector equation for the second eigenvalue by x1 transpose to get x1 transpose A times x2 is equal to x1 transpose lambda 2 times x2. We call that equation B. Now if we subtract the transpose of equation A from equation B, we get that lambda 2 minus lambda 1 times x1 transpose by x2 is equal to 0. Okay. Now if lambda 2 is different from lambda 1, then that means that x1 transpose times x2 must be equal to 0. Now remember that x1 transpose times x2 is the scalar product. It's the product of the x components plus the y components plus the z components, which if these were vectors, which they are since they're eigenvectors, would be the dot product. In other words, the eigenvectors of A are orthogonal when their eigenvalues are distinct. As I mentioned, the magnitude of the eigenvectors is arbitrary, so we always make them unit vectors by normalizing them so that x1 transpose by x1 is equal to 1, etc. Now if we stack the three eigenvectors as column matrices into one square matrix, then we get a special matrix called the spectral or modal matrix. So here I've defined it as P transpose is equal to x1, x2, x3. So the three column matrices representing the three eigenvectors as three columns of P transpose. From the orthogonality of the eigenvectors, it's easy to show that the matrix P is also orthogonal. In other words, P transpose times P is equal to I. And then from the fact that A times x1 equals lambda 1 times x1, we can show that the matrix A times P transpose, which would therefore have columns A times x1, A times x2, and A times x3, must also have columns lambda 1 times x1, lambda 2 times x2, lambda 3 times x3. And then making use of the orthogonality of those vectors, in other words, making use of the fact that xr transpose times xs is equal to 1 when r equals s and 0 when r is not equal to s. In other words, it's equal to delta rs, the Kronecker delta. We can show that P times A times P transpose is equal to the diagonal matrix that has the three eigenvalues along the diagonals. So this is called the spectral decomposition. And shows you that the problem of solving for the eigenvalues is equivalent to the problem of A, is equivalent to the problem of finding the modal matrix that will transform the components of A to be the matrix with the eigenvalues along the diagonal. Now remember that P is orthogonal, in fact it's proper orthogonal, so P represents a rotation. So we can think of the spectral composition as saying there exists a rotation that can be applied to any matrix that will diagonalize that matrix. Now remembering that matrices are components of tensors, and that as you change your frame of reference, perhaps by rotating your axes, you get a different set of matrix components for the same tensor. This suggests that there's always a frame of reference in which you can view a tensor whose components are symmetric as diagonal. And those are called the principal axes. Now another property we can make use of, and you've probably recalled from the past, is that if we multiply a squared times x, then that would be lambda times ax, which would therefore be lambda squared times x, which implies that if lambda I and xi are eigenvalues and eigenvectors of A, then the eigenvalues of A squared and must be lambda squared, and the eigenvectors must be x. So in other words, if lambda I are the eigenvalues of A, then the eigenvalues of A squared are lambda I squared. If xi are the eigenvectors of A, then xi will also be the eigenvectors of A squared. And in fact, we can show this for A to the n. If the eigenvalues of A are lambda I, then the eigenvalues of A to the n are lambda I to the n. And if the eigenvectors are x, then the eigenvectors of A to the n are also x. This allows us to write that the trace of P times A times P transpose, which we've already seen is the matrix lambda 1, lambda 2, lambda 3 on the diagonals, must be lambda 1 plus lambda 2 plus lambda 3. And by extension, the trace of P times A times P transpose squared must be lambda 1 squared plus lambda 2 squared plus lambda 3 squared. Now the trace of P times A times P transpose could also be written as Pij, Akj, Pik, but since P is orthogonal, Pij, Pik is delta Jk, so that means that the trace of PA, P transpose is equal to delta Jk, Ajk is equal to Akk, or the trace of A. So in other words, the trace of A is equal to the sum of the eigenvalues. As an exercise, you can use the results above to show that the trace of P times A squared times P transpose must be the trace of A squared, which must be the sum of the square of the eigenvalues, lambda 1 squared plus lambda 2 squared plus lambda 3 squared. These results in turn allow us to show that the characteristic equation for A, that cubic equation, can be expanded to lambda cubed minus lambda 1 plus lambda 2 plus lambda 3 times lambda squared plus lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1 times lambda minus lambda 1 times lambda 2 times lambda 3. And if we look at this a little more closely, we see that the coefficients of lambda squared, lambda, and the constant will be trace A, trace of A squared minus the trace of A squared, and minus the determinant of A. So these are called the principal invariants of A. Let's just review this. This is the characteristic equation expanded in terms of coefficients of lambda squared. So the characteristic equation will be lambda cubed minus the trace of A times lambda squared plus 1/2 of the trace of A all squared minus the trace of A squared times lambda minus the determinant of A. So these coefficients, trace A, this expression, and determinant of A, are called the principal invariants of A. Finally, let's just review the concept of positive definiteness. The matrix A is positive definite if the product of the column matrix X transpose, the row matrix X transpose, times A times the column matrix X is greater than 0, for all values of x not equal to 0, which in turn implies that lambda 1, lambda 2, and lambda 3 are all greater than 0. So in other words, if lambda 1, lambda 2, and lambda 3 are all greater than 0, then you can say that the matrix A is positive definite. So that's a good place to stop for today.